Hello and welcome everyone to part 2 of our iBwave and PCTEL webinar, Stepping Through an In-Building Project Lifecycle, where you will learn through concrete examples and live demos about the best practices and cost-saving techniques for efficient project management during each step of an in-building project. First of all, I would like to introduce our speakers today. From iBwave, we have Nazim Chaudhry. Nazim is the sales engineer at iBwave. He is responsible for supporting sales engineering projects for the US. He works with customers and potential customers to ensure that they have a firm grasp of the iBwave product suite. Nazim holds a bachelor's degree with a specialization in engineering and computer science from Concordia University. From PCTEL, we have Scott Clay. Scott is the Senior Director of Engineering Services. He has over 19 years of progressive experience in design, commissioning, optimization, and management of RF engineering services at companies including PCTEL and Vision Wireless, Agilent Technologies, and Safco Technologies. Scott holds a Bachelor's of Science in Electrical Engineering Technology from the University of Central Florida. In just a few minutes, we will start the presentation, but first I just want to go over a few housekeeping items. First of all, you will receive the slides and video recording of this webinar as well as of the part 1 of the webinar by email within the next few days. Also, thank you everyone for sending all the questions during registration. If you have additional questions during the webinar, please feel free to type them in the GoToWebinar questions box, and we will get to as many as we can during the last few minutes of the webinar. On the agenda today, we have some introductions to iBwave and PCTEL. Then our presenters will give you a brief overview of what we covered in part 1 of the webinar, and then take you through to the last steps of the in-building project, and then we will go to closing remarks and questions and answers. Now I will pass it over to Scott for our PCTEL introduction.
Thank you, Amna. PCTEL is a telecom solutions company that provides RF engineering services and products to the wireless industry. We are comprised of 2 different divisions: our Connected Solutions division, which focuses on the design and manufacturing of RF antennas, as well as providing kitted solutions for wireless networks. Our second division is our PCTEL RF Solutions division, which is where I come from, and it's comprised of 2 groups, and the groups would be our Network Engineering Services. Our Network Engineering Services focuses on the services that would be provided throughout the life cycle of a network, to include network benchmarking, baseline testing, CW testing, design, commissioning, optimization, acceptance, PIM sweep and fiber, interference mitigation, and finally consulting. On the product side, we focus on our high-end scanning receivers, and we have launched our Flex portfolio of receivers, which include the IB Flex, the EX Flex, and the MX Flex. These have programmable front ends that allow you to collect data from 150 megahertz up to 6 gigahertz for all technologies deployed today. We also have our Seahawk data collection platforms and our Seahawk Touch platform that allow us to collect data while utilizing our scanners. We also have Seahawk Analytics, which allows us to analyze the data and do trending with the data, not only from our scanners, but from network elements as well. We also have our C-Wave product for interference mitigation and interference hunting, which allows us to hunt down interferers not only on DAS networks, but as well as macro systems. And finally, we have our PCTEL Seahawk transmitter that is a multi-band 4-port transmitter that we can utilize for DAS commissionings and turning up DAS networks, as well as any outdoor type low-powered CW systems. At this point, I'll go ahead and hand it off to Nazim, where he can do a brief overview of iBwave.
Thank you, Scott. So a little bit about iBwave. So iBwave is the standard for in-building network design and documentation. So it's been a leading mover in this dynamic and fast wireless growing industry related to in-building systems. So it's been trusted by 700 customers in more than 85 countries worldwide. Now, it's our clients that have been testing this application. They've been using it. They've been successfully deploying it. And they're the ones that are mentioning that this is the best-in-class tool for any in-building wireless deployments. So as you can see, our customer base revolves around the entire in-building ecosystem. So we have our Tier 1 operators, we have all of our operators, equipment manufacturers, as well as system integrators. So we attempted to position ourselves as the common language that can be passed along anyone who's involved in these in-building deployments. Now, since we're dealing with an entire ecosystem, we have several different products to cater for these deployments. And just a little bit about our product suite. So we have an entire portfolio, and really it's meant to address the entire ecosystem. So all these tools are really meant to allow you to plan, dimension, document, and really scale your venue for all these different types of deployments regarding different types of venues. So we have our flagship software, iBwave Design. So this is going to allow you to automate your entire design and planning process. So it's going to allow you to provide valuable simulations and heat maps just to optimize your in-building network. Now, it's not only a prediction tool, it's actually a production tool as well. So as you're designing, the software is going to keep track of everything you're doing, and it could help you create valuable reports such as bill of materials, cost details. So it's going to allow you to make assessments of your design based on cost criteria, based on coverage criteria, and it's really meant to streamline your entire in-building planning process. Now, you may be working with several different projects. You may be working with hundreds and thousands of projects. So it's always a great practice to store and save your projects in a common location. So we also have a network management platform that not only is it going to allow you to store your projects, what it's going to do is it's going to take all the information from that project, crunch all that data, and give you valuable analytics. So we're dealing with a lot of big data these days, so these data are most relevant and most powerful when they're properly analyzed and when they're properly crunched. So iBwave, the Unity platform, what it's going to do is it's going to take in all that data and give you valuable metrics of your deployments. Now, again, as I mentioned, it's a project management platform, so you could visualize all your in-building projects and what's going on with them from the start to the finish of the actual deployment. So we also have a mobile application. So this mobile application really caters to the people that are going to be going out into the field. So in any in-building process, there's going to be a mix between people who are working out at the office and people who are working in the field. So you need a good form of communication going back and forth from the two parties. So the iBwave mobile application is a very good site survey tool that's going to allow you to document all the information you need while you're out there at the venue. And as we saw in the previous webinars, we even had the ability of integrating with collection tools to be able to bring in live walk test measurements of the network, whether it be for baseline testing, CW testing, or validation testing. And we saw in our previous webinar how we were able to collaborate with the PCTEL Seahawk Touch equipment to bring in all that data and apply it to your design. Now, we also have a certification program, so we believe our tools are best used when you know how to use it and you know the technology behind the in-building deployments that you're looking at undertaking. So we have 3 levels of certification, and really meant to make you very familiar with the tool as well as the technology you're using it for. Now, we also have a database of components. Now, up to date, we have close to 16,000 parts. They're all modeled and approved by the manufacturers, and they're ready to be dragged and dropped into the software and be simulated with. So in our previous webinars, what we looked at were the entire life cycle of an in-building project. So we started off by taking a look at network planning and dimensioning. So in our previous webinar, we saw how we could get all our groundwork done. We're going to go out to the venue. We're going to get information about the venue. We're going to get information about the venue, the architecture of the venue, the materials used in the venue. And also what was important is we saw that we could integrate with the PCTEL Seahawk Touch equipment just to bring in all that valuable baseline information for different frequencies and for different bands prior to your design. So once we got all our information from the venue, what we did was we took it back into the design tool and we applied all that information, all that interference baseline testing, and we were able to come up with a design that's going to meet our expected KPIs for our actual end clients. So what we did was, in the next phase, in our detailed engineering phase, is we took all that information, we modeled our venue, and we created a preliminary design, and we validated that that preliminary design was meeting all the expected KPIs for our end clients. So again, in this webinar, we're going to continue looking at the life cycle of an in-building project. So as I mentioned before, the first two steps we looked at in the previous webinar were really the planning and dimensioning phase, where you go out to the venue, you get all your groundwork done, you get a good understanding of the venue, where you have feasible potential locations where you could place your equipment, and we also looked at the detailed engineering phase, where we took all that information from the field and we modeled a replica of the venue, and we created a design to accommodate for the end results and the end KPIs that we wanted to achieve, all leveraging information that we got from the PCTEL Seahawk equipment for your baseline testing. So in this next webinar, what we're going to look at is, after the detailed engineering is done, we have our preliminary design. We want to take a look at installation and commissioning. We want to validate our network, and we want to see how we could operate and maintain our network as well. So I'm going to pass it back to Scott now, so we could go over the installation and commissioning phase.
Great. Thank you, Nazim. So today we're going to go ahead and speak about the installation and commissioning phase here next, which once installation is complete, there are really 4 different tests that really need to be done to ensure that the DAS is installed and performing properly, as well as making sure that the carriers, once they bring their base stations in, are set up properly to communicate with the DAS and connect to the DAS. And then we'll do some handset network element testing. So we'll touch on uplink and downlink testing, pre-integration CW testing, network commissioning, and then finally, as I mentioned, the handset network element testing. So the purpose of uplink and downlink testing is to verify cabling and infrastructure equipment, as well as making sure that they are not only installed correctly, but we're seeing the proper losses associated with each of these components. We need to set the uplink and downlink gains at this time to ensure that the system is configured properly and is ready to accept a base station from the carrier. In order to do that, we initially start with the uplink verification. And the uplink verification validates the performance of the uplink path. It really focuses on making sure that the fiber connections from the remote units are functioning properly and have the minimal amount of loss associated with them. In order to do this, we would adjust the system to unity gain and then inject a known signal either over the air or directly into the remote unit, and then measure that signal back at the head end to ensure that the proper levels are coming out of the head end and we have the expected losses associated with that network and that DAS performance network. We also look for path balance between the MIMO ports. So we make sure that path A and path B have comparable losses associated with them so that we know that both paths are performing consistently together. If they're not, that would result in poor throughputs in your network, and that's certainly something that we really don't want to see. So we want to maximize the throughputs and make sure that this performance is performing properly. In order to do this, we export the link budget information from iBwave and bring it into a spreadsheet. And these results should be recorded in that spreadsheet as well to ensure that we are within the tolerance of the design. So it's very important that these data that are collected during this phase are reported in this workbook and are referenced to the link budget coming from the iBwave design. During the downlink verification, we validate the performance of the downlink path. It's very important that we look at both paths because they each ride on separate fibers. So we want to make sure that we validate the entire path. During the downlink verification, we also validate all of the antenna paths. So we look at every single coax, not just one per RU. We look at every single antenna location, making sure that they are performing and meeting the link budget that was provided to us from iBwave. In order to do this, a known signal is injected in the head end. With our 4-port transmitter, we're able to light up both MIMO paths at the same time. So we can look at those at the exact same time on 2 different frequencies and ensure that they are performing properly. Once this known signal is injected, we go ahead and do a walk test under each antenna. We verify that the signals coming through the antennas are what we expect to see, calculating path loss between the distance of our antennas that are mounted in the ceiling to our antennas that are receiving into our receiver. And we look at the MIMO paths as well to make sure that they are balanced. Again, these results should be recorded in that spreadsheet that has the link budget information provided by iBwave. Pre-integration CW testing is really the purpose is to make sure that all of the antennas and all of the coax are installed properly. But it also verifies the downlink coverage, the intended coverage of the entire venue, to make sure that the design has been implemented properly and that we're meeting the specifications of that design. We verify power settings as well as the MIMO paths. So we walk this entire building to ensure that what the coverage in the building is to what the design specifications were called out in the design. And this is a direct input into iBwave in order for them to validate that design on their end as well. The next stage is network commissioning, and the purpose of this is to verify that the wireless service provider signals are at the proper level before connecting to the DAS. So it's very important that we don't come in too hot or too strong of a signal and overdrive the front end of that DAS. So we want to make sure that we measure all of those signals on every single frequency as well as every technology that will be connected to the DAS. We verify that the attenuation and gain settings are correct based on the service provider's criteria, and we verify the system performance once all the WSPs are commissioned on the DAS. So commissioning and integration is performed once the system verification is complete. System verification is that uplink and downlink testing to prove that the DAS is functioning properly. Now that we know that is done, we are ready to commission the wireless service providers and their base stations onto that DAS. So the base station output power is measured and proper attenuation is set prior to connecting to that DAS. Once those levels are set and the base stations are connected, we will do an uplink gain adjustment. And what this does is it adjusts the gains on the uplink to minimize the noise coming from the DAS into the base station, so that we look at the noise floor on the base station to ensure that we are at the lowest noise floor possible. And what this does, it allows the throughputs to perform at peak performance. And finally, we do a handset and network element test. We go under each antenna and we run some speed tests and make sure that we are able to download and upload files, make sure that our throughputs are performing to the way they're expected. We want to make sure that the proper PCIs, scrambling codes, and PNs are coming out of each antenna in the right locations. We want to make sure that our power levels are set properly and that our MIMO paths are also working properly. At this point, I would like to hand back off to Nazem, where he can show you how to update the design to the as-built configuration in iBwave.
Thank you, Scott. So before getting into this phase, what I really want to talk about is just the discrepancy that can occur between the planned design versus reality. So in many cases, you're going to have a design that was done in iBwave design, and once you go back into the field, you're going to see that this design may not actually be feasible, because when you go out into the field, you might encounter several different restrictions. You may come to an antenna and you may see that there's no way I could really place my antenna in this location. There's some restriction involved. Or I may see that there's some construction restriction, or maybe the property owners, they don't want you to place any equipment in this location. But whatever the case may be, there can be several restrictions that can deviate your design from what it's meant to be in the design platform. So your installation may not always replicate exactly what the designer had in mind. So it's very important at this phase that there's good communication between the field technician as well as the RF engineer, just to ensure that not only are you going to have an optimal design, but you're also going to have an optimal and feasible design. So in this case, the key here is to have good communication going back and forth from the parties involved. So I want to quickly show you where we left off and how we could address this using both the design tool as well as our iBwave mobile application. So I'm going to share my screen now. And really where I want to start off is where we left off in the last webinar. So in the last webinar, we saw we had the ability getting all the information from the field. We were able to leverage the PCTEL Seahawk equipment to bring in all the baseline measurements, and we were able to accommodate those measurements and address any interference that was coming in to create a valuable design that was meeting all our end clients' KPIs. So that was our first step. What we focused on is we want to create a system, meet all the KPIs, and properly model that system to what we saw out there in the field. Now the next step would be to validate the feasibility of this design back in the field. We want to make sure all the components are in appropriate feasible locations, and if not, we're going to have to make some slight adjustments. So what I'm going to do is I'm going to take this project back, this project here, and I'm going to send it all to the field technician so he could open it up in his mobile application. So right now I'm back on my Android-based tablet where I could download that project, and I can open it up directly. So keep in mind you're always working on the same file just so there's always consistency. So what I was working on in the design tool is the same file I'm working on here on my mobile application. Now the first thing you might want to do is take a look at the logical diagram while you're out there in the field. So this is going to help you with your installation because you could see all your equipment. You could see your splitters, your antennas, you could see your attenuators, your head-end equipment, and you can see how they're supposed to be connected. So while you're installing, you have some this logical diagram to reference to. Now what's also very useful is in many cases when you're installing these systems, you might encounter some type of faulty equipment, maybe something that's not transmitting or something that's not working properly. So it's always very useful to be able to label that right there and then when you see that that equipment is not properly functioning. So what I did here was I dropped a push pin similar to what we saw before, and this push pin allows me to document what's going on with this equipment here. So if this antenna here was malfunctioning, I could just mention that I could drop a push pin, take a picture of the equipment, take a picture of the connection of the equipment, take a picture of the product key, or I could just mention that this equipment needs RMA. So the goal of this push pin is just to document anything that's going wrong with any of your equipment. Now next what I can do is I could come back to my floor plan and I could see that I now have access to the entire design as it was created in iBwave design. So the first thing I want to do is I want to come to the venue and validate that these components are in feasible location, that these cable routes are following appropriate paths. So that's what I'm going to do. I'm going to come to this first antenna, and if it's in a feasible location, that's perfect. I can leave it as it is. If the cable routing is taking the right path, then that's perfect. I can leave it as it is. But if I come to another antenna here, and I see that there may be a type of restriction here, maybe the property owners did not want me to place an antenna here, so I need to make a slight adjustment. So what I can do directly from the field is I could quickly adjust that component to a location that's actually feasible. And again, in many cases when you're out in the field, you might have to make adjustments to the cable routing so it'll take and follow an appropriate path, so I can make that adjustment here as well. Now again, as I mentioned before, it's very important that you have appropriate communication with the RF engineer, because we just made a change to his or her design, so we want to get their approval before going out with the installation. So what I'm going to do, since I made a change, I'm going to click on this button, I'm going to upload it back, and it's going to send it directly to the RF engineer. And they have the capability now to either approve or reject those changes. So quickly back to the RF engineer's perspective. On their end, they're going to get a notification that changes were made, and they have the ability of either accepting or rejecting those changes. So I could click on Show, and if I click on Accept, it's going to show me the changes that they made out in the field. And if I unaccept it, it's going to go back to its original location, and same goes for the cable routing. So here I have the ability of either accepting or rejecting any of those changes. And again, the goal here is just to streamline the communication between what's going out in the field and what's going out in the venue. Now keep in mind you could also associate the changes with a pushpin and document really why you made that change as well, just so the RF engineer could better understand what's going out there. So at this point I'm going to pass it back to Scott so he could take us through the next step in this deployment process.
Great. Thank you, Nazem. So now we're going to talk about network verification and as-build. The system has now been installed and commissioned. The carrier's on the system. So where do we go from here, and how do we make sure that the system is performing properly? There are several tests that we'll run during this phase: the integration testing, post-deployment baseline testing, and then finally a network benchmark. So the purpose is to verify the system performance to the design specifications. That's really all our goal. We know that the design was approved by our end customer. We want to make sure that now the system is built to those specifications, that we can verify the KPIs for coverage, quality, and throughput, verify our neighbor list, soft handoff percentages and soft handoff areas, verify uplink performance based on UE transmit power. We want to make sure that the macro cell power adjustments, if there were any required, have been completed so that we don't have bleed over into the building unnecessarily from the macro networks. And we verify the MIMO paths again via UEs and making sure that those paths are performing properly. The typical KPIs that we'll look at for each technology: with LTE, we look at the reference signals for power and quality. We look at RSSI 0 and RSSI 1 for the MIMO paths. We look at UE transmit power to make sure that the uplink performance is correct, as well as throughput, and also, very importantly, PCIs. We want to make sure that the PCIs that are coming out of the base station into the DAS are properly set, and that we make sure that these PCIs are dispensed throughout the venue according to the sectorization plan. If this is not happening, then your handoffs will not work properly, and there will be a lot of issues with handovers, especially in the egress and ingress portions of the venue where you're trying to hand out to the macros and back into the macros, walking it to and from the building. For UMTS, a very similar set with RSCP, UE transmit power, and primary scrambling codes. For CDMA and EVDO, we look at EC, transmit power. We look at active pilot count to make sure that our coverage is in the intended areas and we don't have too many pilots in the CDMA into the UE, which would degrade the capacity as well as using too many network elements. We look at EVDO throughput, and we also make sure our PNs are in the proper location, and then looking at quality with FER. For GSM, RxWev, RxQual, transmit power, and again the channelization through BSIC and BCCH. So this is the perfect opportunity to look at optimizing this DAS network. The base stations are now connected. We know that DAS is performing properly, but we want to make sure that the RF is in the proper areas and that the loads from the base stations are correct as well. So at this point, we would provide optimization recommendations, and we would verify and optimize power settings. We want to look at and correct the parameter loads if they are incorrect, looking for wrong PNs, scrambling codes, PCIs, making sure that's correct, and especially looking at incorrect neighbor lists. If there are macro sites out there that should be in the neighbor list and they're not, that would create drops in the egress and ingress points. We don't want that to happen. We also want to make sure that we look at the coverage coming from the macro cells on a scanner to make sure that there's something that's not missed. UEs get all their information from the network. They're told what to look for. whereas a scanner actually scans all the RF in the air. So it's very important that you utilize both UEs and scanners during this optimization phase to make sure that you get a true picture of the RF signal that's in the air, and that you can make adjustments to that so that you can optimize not only your DAS performance, but the entire network's performance. Occasional antenna adjustments could be made, especially in soft handoff areas. You want to minimize that soft handoff to make sure that you're not using too many network elements and you're getting better spectral efficiency on your network. A post-deployment baseline may be required as well. This is used to verify that DAS dominance. You want to make sure that your DAS is dominant within the venue that you've intended it to coverage, but you don't want that dominance outside of that venue. You don't want it taking on traffic outside of the venue that the macros should be covering. And on the converse side of that, you also do not want your macros taking up some capacity from that venue as well. You want to make sure that you have good cutoffs between the macros and the DAS so that you get optimal performance from both. The scanner will provide a clearer picture of the macro bleed over into the building as well as the DAS bleed over out of the building. It can be used to optimize handoff candidates or macro site parameters and antenna tilts and azimuths. If the network neighbor list is not correct, the UEs won't see that, but the scanners will, and you may be missing a handoff candidate that is out there if you utilize a scanner that allows you to identify all of the candidates that you would want in your neighbor list. This also provides a view of the DAS performance on a carrier-by-carrier basis. This allows us to make sure that all of the carriers on the DAS are performing properly. And if there's some carriers that are not on the DAS, some wireless service providers that have chosen not to join the DAS, this could be a way to persuade them to go ahead and join this DAS network at a neutral host environment so that they get better peak performance in that venue as well. It also provides a snapshot of the DAS at its peak performance. This DAS was just optimized, it was just turned up, it was just verified, so we know that all of the components are performing properly. And this provides that snapshot at its peak performance so that later down the road when you go to make sure that you're doing your verification checks that you know that this is it's continuing to perform at its peak performance. At this point I will go ahead and hand back off to Nazem where he can talk about how to bring this information back into iBwave.
Thank you, Scott. So at this point, what I want to speak about, so Scott was mentioning how it's important that we're going to have to bring in a lot of measurements and validate that our actual system is performing to its design. So really what we do in this phase is we're going to go back to the venue, and once the system is turned up, we're going to do another walk test. And this is just an example of some of the metrics we want to pull in, some of the KPIs we want to validate for our actual design. So we're going to perform a validation walk test, and we want to see how in line our actual system is with the design we actually specified for. So again, in our design, we specified that we're going to be meeting all these KPIs and all these targets. Now at this point, we want to validate that our real system is going to meet those as well. So aside from that, also what we want to focus on is once we've completed our installation and we verified our network, we also want to ensure that we're getting complete as-built documentation. So we've made some adjustments before. Now we want to make sure that we keep track of every adjustment that we've made during the installation because we want to have complete, accurate as-built documentation. So any antenna changes, any orientation changes, any down tilts, any cable changes, any cable path changes, any of your equipment that was moved slightly, we want to make sure we capture all that information. At the end of the day, we have a good geolocated, detailed as-built documentation, and we want to make sure that it's as accurate as we see it in the venue. So really what I'm going to show you now in this next phase is how we could make sure that we could validate our network and we can also capture all our as-built documentation. And we're going to see how we could streamline the generation process of some of these very tedious documents that you have to create, such as your closeout packages, or different documentation packages that you need for your end clients or even the property owners. So I'm going to share my screen now. And I'm going to go back to my design that I was working on previously. So what we saw here is we made some slight adjustments, and we made some slight adjustments, and the next step would be to really validate our design. So if you remember from our previous webinar, we saw how we could integrate with the PCTEL Seahawk Touch equipment. So by clicking on this icon here, what you have the ability of doing is you could integrate with a supported collection tool. You're going to be able to bring in all the measurements that you've taken and bring it directly back onto your floor plan. So in this scenario, what I did was I clicked on this button here. It opened up the PCTEL Seahawk Touch equipment, and I was able to bring in my validation walk test directly onto my floor plan. So as you can see here, I have that survey information available. And here you can see in this case, before I had my baseline testing, but now I'm doing my validation testing. So keep in mind we're working on the same file from the beginning of the process. So on this same file, I have my CW testing, I have my baseline testing, and now on top of it, I've added my validation testing. So you could fall back to any of your measurements, and they're all being stored on this same file. So the first thing I did was I did a validation walk test, and already I could start visualizing it directly onto my mobile application. So I could see closer to the antenna. I saw the signals were close, were much stronger, and they got weaker as I got further away from the antenna. So again, you could validate with the legend that we have up here. So areas where it's more reddish is somewhere near -55, and as it got further away, you could see the signal got a little weaker and weaker. And again, closer to this transmitter, I saw that my signal was stronger as well. So already we have the ability of making a quick visual assessment that our system is up and running properly. Now the next thing I might want to do is I want to make sure I capture good as-built documentation for all my components. So once we validate that our network is working properly, what we might want to do next is just capture all our as-built information of all our components in place. So already our components are being geolocated, but in many cases during our installation and our commissioning phase, there may be some slight adjustments that took place, some down tilts, some orientation changes. So we want to make sure that we capture all this information directly while we're already there at the field so we could verify it. So again, by clicking on this antenna here, I could put in all that as-built information in this electronic type format. So I could change my heights, any azimuth changes, any down tilts, any orientation changes. I want to make sure I properly capture it. And my end goal is I want to have my documentation replicate exactly what's in there in the field. And same goes for my cabling. So previously in my design, I may have saw that I needed 40 feet of cable, but in reality, I might have seen after doing some measurement testing that I actually needed maybe 42 or 43 feet. So again, I could replicate that here in my length. So again, the goal is just make it as accurate as possible as it is in the venue. And the same goes for any of my components. Now, the next thing we might want to do is we might want to take actual physical documentation of the equipments in place. So what I can do is I could quickly access my push pins again like we saw in the previous webinar. And this time I'm going to focus on taking pictures of my equipment that have been installed. So I could have as-built pictures as well to go with my documentation. So again, here I had an antenna, so I dropped a push pin. And again, with the push pin, you can associate any type of documentation. It could be a picture, a text message, a video message, or even a voice message. And in this case, I just quickly snapped a picture of the antenna. And I took a picture of where it was mounted. Again, if you want, you could quickly use a pen and highlight different information directly on the picture as well, or just take different notes directly on the picture. So now that I have all this information, again, as in all the previous steps, what I want to do is I want to send it back to the designer so he could start building all these valuable reports for himself or for the end client. So again, I'm going to do the same thing as I did before. I'm going to click on this upload button here, and it's going to go back to the designer. So here you can see I sent all that information back to the designer. Now one thing you can do, since you already have your validation walk test, is you could start making comparisons with the actual prediction. So what I did was I brought in my validation walk test, and on top of it I'm overlaying my prediction, just so I could validate how accurate my design was with regards to the real life values that I saw. So again, if I come back to my design, I could see the areas where I saw the signal was near -71, and this is RSRP. I could see that my prediction was also very similar. So here I see it was close to -73, and I could validate it for every single one of these points as well. So it's a quick way of just validating that your design in reality was really propagating the way you actually designed it for. Now we also saw that we brought in a lot of as-built information. So now the goal would be to really streamline all those tedious documentations that you have to do after a design. And what we've added here is several different functionalities. So I could come to reports, and the first thing I might want to do is just pull a report of all my physical pictures that I took of the venue, associating them to my actual equipment. So I could pull this annotation report, and what that annotation report is going to do is it's going to streamline that whole documentation process for all your actual as-builts. So here I can see I have my floor plan and I have it associated with different reference points, and we can see the pictures associated to those reference points. And again, here if I come to 3, I could see that this is where my antenna was placed, and I can come back down and come to 3 and see my as-built pictures for my actual antennas. So again, here we can see that we have a blank template, but what you have the ability of doing is you could customize this template to your own standards, to your own company backdrop, and it's just going to be another level of automation. And if you want, you could also export it into several different formats. It could be a Word, it could be PDF, it could be PowerPoint, and the goal here is just to streamline a lot of that tedious work that you had to do. So previously you'd have to take your digital camera out, extract all your pictures, resize them, relabel them, reference them. So we want to just quickly streamline that process. Now again, keep in mind, as I mentioned before, we're always working on that exact same file. So throughout the entire deployment process, we did a lot of survey measurements. We did our baseline, we did our CW, and we did our validation. But all this information is still being stored in this exact same file, even as it was going back and forth from the field to the RF engineer in iBwave design. So at any point in time, if we want to access that information, I can come to reports. And let's say I want to pull a survey data report. What I can do is I could just pull a report of all those survey measurements I pulled through my deployment process. So here I have an example of a survey data report. And here you can see I have my CW testing. I have my baseline testing as well. I have my validation walk. So all those metrics that I was able to leverage from the PCTEL Seahawk Touch equipment, I could just quickly batch print it out as well. And again, if you want another level of automation, as I mentioned before, you could change the backdrop and really customize it to your company. And finally, a last report that may be very valuable. So since you validated your design and everything is good to go now, you might want to just quickly highlight all the different heat maps that are showing that you've actually achieved all those different KPIs. So my last report would be a batch output map design report. And really what the goal here is you want to select all the different heat maps that you want to just quickly batch print out. So I could select maybe 5 or 6 heat maps. And what it's going to do is it's going to automatically generate this output map report with all those KPIs that I selected, whether it be my signal strength, my SNIR, my data. So all the heat maps that I want to pull, I could just click on them and it's going to generate this automated report. So as you can see here, the goal was to really streamline a lot of those tedious documentation processes that you have to do after you're done completing your design. So at this point, I'm going to pass it back to Scott so he could talk a little bit about operations and maintenance.
Great. Thank you, Nazem. So the last phase of the network lifecycle is operate and maintain. This is a very important phase. There's constantly network troubleshooting that would happen. if there's any system failures. Interference management, as carriers or people in areas turn up unknown signals and signals that would impact the performance of your network. So you may need to do some interference hunting. And finally, the network benchmark. So the network benchmark is really the main test that we would perform during this phase. So yearly maintenance should be performed. A lot of different companies use different schedule, whether it's yearly maintenance or quarterly maintenance or biannually maintenance. But it's very important that this maintenance is done in order to maintain the performance of that network at its peak. Network benchmarking is performed to verify all antenna locations are still performing properly, so a walk of the venue would be required. It provides a comparison to the initial benchmark that was done during acceptance testing. So this allows you to trend that data, whether you use an analytics tool or something of that nature. This allows you to trend that data to make sure that your network is still performing at its peak performance. You should always inspect the head end and the remote locations, making sure that all connections are still torqued properly, that there are no kinks in coaxes, and that makes sure that everything in there is performing properly and there are no alarms on the system. Any issues should be reported and repairs should be made. Anytime you do a carrier add, adding an additional carrier or technology to that DAS network, it's very important that you bring in commissioning people that are certified and understand how to commission that additional carrier on the DAS. If you don't, that could impact the other carriers that are on the DAS. Every carrier is allotted so much power and percentage of power on a DAS network. You want to make sure that you're not stealing from one carrier and reducing their coverage footprint by adding another technology or carrier for another wireless service provider. So I want to go through some closing remarks. In summary, DAS and small cell networks require multiple phase testing and optimization approach for successful deployments. It's very important that all of this testing be done. Okay, there's multiple tests that we run. We run tests to make sure that the DAS itself is performing properly prior to putting on any wireless service providers or attaching any base stations. This proves that the DAS is good, so once you add a base station, then you know if there are any issues. It could be on the base station side of things, and that kind of narrows the approach of making sure that everything is optimized. DAS and small cell tests require proper engineering tools. As I mentioned, we utilize UEs to look at transmit power on the uplink. We use UEs to show us what the throughput is of that network and it's performing properly. But we have to use scanners as well to take an outside look of the network to make sure that we see all of the RF that's in the air and make sure that stuff that's not intended to be on the network is not impacting our design. So if we're seeing other sites come in, we can optimize those sites and make sure that we have a true clean signal in our venue. We want to optimize RF first and then optimize other characteristics of the network. If your RF portion of the network is optimized, if your soft handoff zones are minimized and everything else is good, then you know at that point it's usually parameter changes that you would have on your base station in order to make this system together perform at peak performance. Successful DAS and small cell deployments require multiple iterations of testing for integration walk test for best spectral efficiency. As we mentioned, the integration walk test may be done multiple times as you optimize different parameters, as you change azimuths and down tilts. You want to re-walk that to make sure that those had a good effect on the network, that the network is now performing better than it did prior to those changes. And any time you make parameter changes as well, you would like to do another walk test to verify that those changes are good. At this point, I'll hand it back off to Nazem so that he can have some closing remarks of his own.
Thank you, Scott. So just some key points to remember throughout the two-part series of this webinar. what we saw was that whatever the venue or type of in-building system that you're working with, whether it be a DAS or small cell or Wi-Fi system, usually there's several people getting involved. And the key here is you want to have a good coordination of work and and the flow of information is always key. And this is one of the reasons why we saw the importance of integrating both of our applications with the iBwave application with the PCTEL touch equipment, because we want to have a good flow of information. So we're out there in the field, we're collecting all this information, and it's also important that we get live, we actually collect measurements and metrics from the field and put all that information together so you have a good coordination of the work as well as a flow of information. So at the end of the day, an in-building site is going to become a living entity of the operator's network, and it's going to evolve over time. So at the end of the day, the industrialization of in-building process will always warrant optimal deployments and scalability. So just thinking about it, we may have completed a venue, but we saw how important it is to maintain that venue, because we are working with a living entity now. So in the operators networks, a lot of things can happen. Maybe the outdoor macro network may have been optimized, maybe some powers have been adjusted, maybe some down tilts have been done in the outdoor network, which are impacting your in-building system. So it's always important that you have good documentation to fall back on. So if at any point in time there was an adjustment that was made to the outdoor network, maybe even a small cell was placed nearby, we want to be able to fall back into our existing design and make those adjustments. So this is regards to any adjustments that are made, but also keep in mind we are working on a specific technology today, but in the future we may be coming back to the venue to rework it to add another technology. So it's always a very good process, very good practice to have all that information stored in a centralized location that you could always fall back on. So maybe today I have 4G, but tomorrow I might want to add Wi-Fi. Later on I might want to add 5G. And this becomes very simple if you have the that same project to fall back on, because already you have the existing system designed, you have it in play. So adding another technology or expanding to it becomes much more easier, because you already have a lot of the groundwork done in those previous phases. So with that being said, I just want to thank you all for attending this two-part series. For those of you who have not seen the first part of the series, I would suggest that you're going to receive an email with both of these parts. So if you'd like, you can go ahead and download them both and watch them both as well. So I'm going to pass it back to Amna now, as she has some closing remarks as well.
Thank you, Nazim and Scott. And thank you, everyone, for sending us your questions. We do have time to answer a few. So I will quickly read the first one. It's want to learn more how small cell modeling is done at indoor environments.
Thank you, Amna. So I'll answer that question. So really what we saw in this two-part series is very similar for the process for DAS and small cells. So when you think about small cells, really what you need to consider is for each small cell, they're going to be seen as a sector. Now, when it comes to the modeling of the venue and the multi-phase testing, it's going to be very similar to what we went through now, so there's not much difference. But you need to look at each small cell as a sector-by-sector scenario, and also depending on the small cells, there's some different configurations that you need to consider. So in many cases with small cells, you have ingress and egress configurations. So you need to make sure you're addressing those ingress and egress points with the proper grid and gateway configuration. And again, it's very similar to a multi-sector DAS type system in the sense that you need to take a look at some of your overlapping zones between small cell to small cell. But at the end, what we covered in the last few days, or in the last few webinars, sorry, it's going to be a very similar approach. We want to go into the venue, we want to get our groundwork done, we want to do our multi-phase testing to ensure that at the end of the day we're going to have a optimized design with the same end criteria of having dominance inside our venue. Yeah.
Thank you, Nazim. The next question is, how do you validate indoor small cell installations?
I'll take that question. So small cell installations, to validate that, you really want to first look at the backhaul to make sure that the backhaul that's coming to the small cell is performing properly. At that point, it's really very similar to validating a DAS or any other component. You want to make sure that the small cell is able to hand off and into out the macros or other small cells. So you want to utilize some UEs in order to make sure that those handoffs are occurring, the neighbor lists are set properly, as well as the throughputs are good on that small cell. You also may want to look at some scanner information as well to make sure that you have captured all of the handover candidates that you would want for that small cell. So the validation process is very similar once the installation is in. You just want to make sure that it's going to play within the network as it's intended to by looking at scanner data as well as UE data to validate that performance.
Thank you, Scott. And another question we have is about the advantages and disadvantages of active DAS.
Okay, I think you're looking for the difference between passive and active DAS. I can take that question as well. So passive DAS are usually deployed in order to bring additional coverage into a building that may have much larger penetration losses. So you just really want to extend that coverage into that building. You don't really necessarily need a lot of capacity in those buildings, but you just want to extend that coverage. Where an active DAS, when you deploy an active DAS, you're more looking at larger venues where you can put base stations into these DASs and sectorize these active DASs to accommodate more capacity. Venues such as large soccer fields or NFL stadiums or college campuses where you're going to get a large concentration of people. So the difference really is it a coverage or a capacity installation? And at that point, for coverage, you may be able to get away with a passive DAS, whereas for capacity, you would want an active DAS where you could sectorize that DAS and make sure that you can install base stations on each of those individual sectors.
Thank you, Scott. And one last question that we have is, can we do the RF measurements of different technologies like LTE, UMTS at the same instance while doing the walk test?
Yeah, I can take that one as well. Yes, you can. There are a lot of different products out there, UE-based products that are manufactured by companies like ASCOM or JDSU. Those allow for multiple different handsets to be connected to a laptop computer or Bluetooth to a tablet. And you can collect multiple different technologies and frequencies at the same time, as well as collecting data on the scanners. Our PCTEL scanners can do up to 40 different channels and technologies at the exact same time. So this allows us to do a complete baseline and equal comparison of all technologies and all frequencies deployed at the exact same time, which is very important.
Yeah, and then just another point to add to that, Scott. So even in the iBwave mobile application, if you did those simultaneous testings, you have the ability of bringing them all in simultaneously back into both the iBwave mobile application and then into the iBwave design application.
Very good point, Nazim.
Thanks, Scott.
Thank you, Nazim and Scott, and we are out of time. I would like to thank everyone who joined us today and for all your questions. To continue the conversation, I would invite you to join us in our LinkedIn group, the iBwave in-building community. Also, I would like to remind you that you can look for the recording of Part 1 and Part 2 of this webinar and the slide decks from these presentations in your inboxes within the next few days. They will also be posted on our website in the webinars section. Once again, thank you for taking the time to join us today. Have a great day.
Thank you, everybody.
Thank you, everyone.